Hi everyone, this is the second lecture on Ethereum. I'm going to talk a little bit more about states, transactions, and blocks of Ethereum in this lecture. Here is the outline of the lecture. First, I'll explain what the world state is and an account state is made of. Then I'll talk about transactions in Ethereum and the fields of a transaction. Then I will talk about blocks in Ethereum and the elements that are included in the header of a block. Finally, I'll talk about transaction execution, which is the most complex part of Ethereum's protocol. And finally, we'll see the references. Let's start by defining the world state. The world state is a mapping between addresses and account states. Each address is a 160-bit identifier that uniquely represents some node, or we can say some account. And the world state, or sigma, basically maps an account's identifier into some state. So let's say if the account identifier or address is A, then the state represented by the world state for that address or for that account is going to be sigma A. And basically, sigma A is going to be called the account state, which is made of 4 fields. The first one is a nonce, which is a scalar value equal to the number of transactions sent from address A, and then balance is the second field in the account state, which is a value equal to the number of way, or the lowest or smallest denomination of an ether owned by address A, and formally balance is represented this way in the yellow paper of Ethereum, while nonce is represented this way. So sigma A is the account state. If you add a subscript n, it becomes the nonce. If you add a subscript b, it becomes the balance. Then storage is another element in the account state, which is a 256-bit hash of the root node of a Merkle tree. It's a special Merkle tree. It's called Merkle Patricia tree that encodes the whole storage contents of the account, and it is denoted this way. The sigma A sub s is the storage root. And finally, code hash, which is the last element of the account state, is basically the SHA tree or KCAC hash of the EVM code of the account. Basically, EVM code is the code that gets executed whenever the account receives a message call. This hash is represented using this notation, sigma A sub C. As I said, sigma A is basically the state of the account, and sub C, C stands for the code hash. And basically, the code itself is going to be stored somewhere in the state database, but we're gonna use the message digest or the hash value of this EVM code inside the account state to basically represent the state of a given account. And this code is going to be immutable. That means you cannot change it, but other fields of account state is going to be changed when you do different transactions. Now, sometimes you want to represent a special account which we call it a non-contract account. In those situations, we are going to set the code hash equal to the show tree of an empty string, which is represented this way. Next, we talk about an Ethereum transaction, the details of a transaction and the fields inside a transaction. Basically, a transaction which is represented using letter T in the Ethereum's yellow paper is a single cryptographically signed instruction that is constructed by an actor externally to the scope of the Ethereum. And when we say an external actor, we either mean a human or like software tools which will be used in the construction and dissemination of transactions. There are two main types of transactions. One type is basically the ones that result in message calls that are created and exchanged between existing accounts, or those resulting in creation of new accounts with associated codes. We call those transactions contract creation because they create new contracts, and or they create new accounts that have EVM code in them. Now, let's talk about the fields that are in a single transaction. The first one is nonce, which is a scalar value equal to the number of transactions sent by the sender, and normally this is going to be represented using T sub n, because n stands for nonce and T stands for transaction. The next field is gas price, which is a value equal to the number of ways to be paid per unit of gas for all computation costs incurred as a result of the execution of this transaction. Formally, we represent this using T sub p. Basically, this is gonna tell you what's the gas price per unit of gas is, and later you will see that for every transaction we're going to consume a certain amount of gas. The next field in Ethereum transaction is gas limit, which is a value showing the maximum amount of gas that has to be paid, has to be used, I should say, in execution of a transaction. This maximum amount is paid upfront before any computation is done, but because it's a maximum amount, it cannot be increased later. So there's an upper bound limit on the amount of computation that each transaction requires. And gas limit is represented by T sub g in Ethereum's yellow paper. Then we have the two field, which is basically the 160-bit address identifying the recipient of the message call, or if the transaction is basically a contract creation transaction, the two field has to be empty, and two field is represented by TT. The value is another field, which is basically the number of ways to be transferred to the message calls recipient, or in the case that the transaction is a contract creation, it's going to be an endowment to the newly created account. The value is represented by T sub v, and then we have VRS, which are the values corresponding to the signature of the transaction. The signature of transaction is will happen using ECDSA, which is a mechanism for digital signature, which we talked about it before, and it was used in Bitcoin as well. And as you see, using these formulas and using these operations that you will see in this slide, we can make VRS public key and private key related to each other, and using some mathematical operations, they can be converted to each other, and that's how the sender of the transaction is determined. Basically, you can retrieve the public key given RSV, and they are used for signing and verification of signatures as well. Other than the fields that we discussed, and it exists in both types of transactions, either the contract creation or message call transactions, we have fields that are specific to a transaction type. For example, in a contract creation transaction, we have the field init, which is basically an unlimited size byte array specifying the EVM code responsible for initialization procedure, which is represented using T sub I, and this initialization procedure results and returns the body of another fragment of code that is used to execute every time the account receives a message call. So basically, it initializes the EVM code of the account, and it's only used once. That's why we call it a initialization. Also, a message call transaction contains data. This field doesn't exist for contract creation transactions. The data is an unlimited size byte array, which specifies the input data of the message call, and the data is represented by T sub D. As an example here, you can see a transaction that shows the recipient, the value, the data, and the signatures, and basically creates a state transition from the current state to the next state. And as you see, different states have different fields with different values in each field. Next, I talk about the blocks in Ethereum and the structures inside the block. A block in Ethereum is made of 3 pieces: BH, or the header, which contains relevant pieces of information. I'll talk about the details of the block header later. Then we have BT, which is basically a sequence of transactions that are basically included in that block. And then BU, which is basically the headers of AMRs. What is AMR? Basically, the blocks that are siblings of the parent of this block are called the AMRs. And the better definition is this: a block whose parent is equal to the present block's parent is called AMR, and all the headers of those blocks are basically combined into the third element of a block, right? What is a block header? A block header basically is a combination of the following pieces of information. The first field of block header is parent hash, which is a SHA-3 or KEKAK 256-bit hash of the parent block's header in its entirety, and it's represented using H sub P. Then we have AMR's hash, which is the KEKAK 256-bit hash of the AMR's list portion of the block, which is known as H sub O, or which is represented by H sub O. Another field in the Ethereum block is beneficiary, which is basically the 160-bit address or identifier of the account that will receive all the fees that are collected from the successful mining of the block, and that's represented by H sub C. Then you have state root, which is the SHA-3 256-bit hash of the root node of the state tree. After all transactions are executed and finalizations are applied, when we say a tree, we mean something like this, not a binary tree, basically a tree in which every node has 3 children, and basically a state root is the root of that data structure. And then we have transactions root, which is the SHA-3 hash of the root node of the tree structure, populated with each transaction in the transactions list portion of the block. If you remember, the block contains all the transactions, and basically this is the digest of the transactions, called transaction root. As you see, this is the root of a tree in which every node has at most 3 children. It's represented with H sub T. And then we have receipt root, assuming that each transaction has a receipt. This receipt root is basically the SHA-3 256-bit hash of the root node of the tree structure, populated with the receipts of each transaction in the transactions list portion of the block, and it's represented using H sub E. Then we have difficulty, which basically is related to the proof of work of the Ethereum. This is the value corresponding to the difficulty level of the block, and it is basically possible to calculate difficulty given the previous block and the timestamp, because it's always a function of the previous block's difficulty level and the timestamp. As you may know, the difficulty will change over time, but it changes using a regular formula that can be calculated. So that difficulty is formally represented by H sub D. Then we have number, which is a value equal to the number of ancestor blocks. Basically, number is required to find out who's the longest chain, and it's basically helping Ethereum miners to determine the longest chain and allow them to reach consensus. We talked about this before. Then we have gas limit, which is a value equal to the current limit of gas expenditure per block. So as you see, the block itself has also a gas limit. Then we have gas used, which is a value equal to the total gas used in the transactions of this block, which is formally represented by H sub G. And then we have timestamp, which is a value equal to the reasonable output of Unix's time function at this block's inception. It's represented using HS. So we're going to assume there's a global clock here. And then we have extra data, which is some arbitrary byte array containing data relevant to the block, and it cannot exceed more than 32 bytes. Then we're going to have mix hash and nonce, which are basically 256-bit and 64-bit pieces of information respectively. The mix hash is a piece of information that proves that we had done sufficient amount of computation that to create this block. Basically, it's a receipt for the proof of work that shows that the proof of work is legitimate. Not only mix hash combined with this nonce, they both will prove that a sufficient amount of computation have been carried out to generate and construct this block. We have talked about this. We have talked about the proof of work of Ethereum previously. Finally, we take a look at the Ethereum transaction execution, which is the most complex part of Ethereum's protocol. It defines the state transition function, assuming that Ethereum is basically is modeled like a state machine. So any transaction that has to be executed must pass some initial tests of validity. The tests include the following. First, we need to make sure that the transaction signature is valid. Then, the transaction nonce is valid, which it should be equivalent to the sender account's current nonce. And also, the gas limit should not be less than the intrinsic gas G0 that is used by the transaction, so that we can pay for the gas of the transaction, and the transaction doesn't need more, let's say, computational power than the gas limit. Also, the sender account balance contains at least the cost required in upfront payment. Please note that after we make sure the transaction is valid and we did all those validity tests, the execution of a valid transaction will begin with an irrevocable change made to the sender's state. The nonce of the account of the sender is incremented by 1 because the sender has just executed the transaction, and also the balance is reduced by part of the upfront cost. As you remember, the gas price times the gas limit is going to be, the maximum cost, and some part of it is going to be charged, and balance should be reduced by that part. The computation of the transaction execution results in an eventual state. We will have a state that is going to be different from the state before doing the transaction, and we are going to do this state transition either if the transaction is a contract creation or a message call. Both types will cause a state transition, and the change is going to be deterministic. It's not going to be random, and it's not going to be invalid because we first do validity test on the transaction. And here is my only reference, the yellow paper of Ethereum written by Gavin Wood in 2014.